Let me start by telling you who we are. So Purigen Biosystems was founded in 2012, and our mission is to develop revolutionary sample prep solutions to help customers get the most out of every sample. We know your samples are important, and we want to make sure that you get all the information that you can from what may be a very limited sample source. Our core technology was invented by Juan Santiago and his team at Stanford University. And we're currently headquartered in Pleasanton, California. You can see from the map, we're surrounded by some of the real giants of the biotech industry. Our investors include 5AM Ventures, Agilent Technologies, Roche Ventures Fund, and Coda Capital. Purigen uses a different sample preparation technology than traditional sample prep methods. It's a method called isotachophoresis, or ITP. And let me walk you through the difference between those two methods. So traditionally, nucleic acid purification is based on surface absorption. The nucleic acid is absorbed onto either a silica-based column or a bead, carboxyl-based bead. And that absorption takes advantage of the differential solubility of the nucleic acid compared to other components in a raw lysate. The disadvantages of this solution is that by absorbing the nucleic acid onto the surface, you're taking it out of its natural environment in solution. And so that can cause the nucleic acid to be damaged by the dehydration process on the surface. You're also at risk of permanently losing the nucleic acid if it doesn't come back off of the surface. Secondly, your downstream eluate is at risk of contamination with the harsh wash solutions that are used to wash other components off of the surface. And lastly, you're at risk of bias. Not every nucleic acid is going to bind to that surface in the same way. In contrast, we use ITP, and ITP is a form of electrophoresis. The principle of separation is the charge, and specifically the charge of the nucleic acid on the phosphate backbone. The advantage of this is that we're simply moving the nucleic acid from one solution to another solution, and so we're keeping the nucleic acid in its native environment. That allows us to achieve high yield and high integrity. We achieve high purity of the nucleic acid by carefully choosing the electrophoretic components that are in the solution. And overall, we're trying to give you the best representation of what's really in your sample. We're trying to purify all of the nucleic acid based on its common property of the phosphate backbone. The result that we're delivering to you is better data. The way that ITP works, I'll depict you in this slide. So we load the nucleic acid into a microchannel that's represented by the diagram on the upper left. We sandwich the nucleic acid in the lysate between a cathodic buffer with slow negatively charged ions and a separation buffer that has fast negatively charged leading ions. We then apply an electric field, and the nucleic acid moves towards the positive electrode. The other negatively charged ions, leading and trailing ions, also move towards the positive electrode, with the leading ions in front and the trailing ions behind. The nucleic acid starts to form a sharp zone between the leading and trailing ions. It can't get ahead of the leading ions because the leading ions are faster, and it can't fall behind the trailing ions because the trailing ions are slower. And so the nucleic acid forms a tight zone that we call the ITP zone. We continue to drive current until the nucleic acid traverses to the extraction reservoir, at which point we turn off the electric field and the nucleic acid can be extracted easily. Purigen has built an instrument around the ITP process, and I want to show you that instrument, the Purigen Ionic. Inside the Ionic, we hold the Purigen chip, and that chip contains 8 parallel channels, each of which independently purifies an individual sample of nucleic acid. What you're seeing here is real nucleic acid dyed with a fluorescent green dye, and run at accelerated speed for demonstration purposes. In the real example, this takes about an hour to run. You can see what's happening, which is that the nucleic acid is being sandwiched between the slow trailing ion in red and the fast leading ion in blue. And you can see the impurities falling behind. We continue to drive the electric field until the nucleic acid reaches the elution well, at which point we shut off the field and the instrument opens, allowing you to collect the nucleic acid with pipette. That nucleic acid can then be taken to any downstream analysis that you want to perform. Together, these two components form the Purigen ionic purification system.